By the end of this video, you will understand what is Euclidean algorithm for computing GCD. We will go through the concept, we will code it. Also at the end, we will look at a sample problem. So let's get started. So what is Euclidean algorithm? See, let's try to understand this algorithm directly by taking an example. Let's say they have given you two non-negative integers, a and b, and you need to compute the greatest common divisor, that is GCD, right? So what is a GCD? GCD is just the largest number which divides a and which also divides b. So GCD of a and b will be commonly denoted as GCD a comma b, right? Throughout this video, we will use this particular representation only. The mathematical definition of GCD is something like this. Maximum value of k greater than 0, which divides a and which divides b. This particular vertical line that you see means k divides a. So this is a mathematical definition. So let's first address the edge cases. Let's say either a is equal to 0 or b is equal to 0. If any of the two numbers that they have provided us is 0, then the non-zero number will be GCD by the definition. See, GCD is the largest number that divides both of them. If any one of them is 0, let's say a is 0 and b is 5, then GCD will be 5 because 5 will divide a and 5 will divide b as well. And this is the greatest value that you can have. So by definition, if any of the two numbers that they have provided, that is a is equal to 0 or b is equal to 0, then the non-zero number will be the GCD. It's very simple, right? Let's say both of them are 0. A is also 0 and b is also 0. Then GCD is undefined. But for the convenience and to keep the associative nature, we will say GCD will be 0 when a is 0 and b is 0. Right? This case can be handled separately. But just to keep the associative nature, we are saying GCD will be 0 if both of them are 0. Now let's look at the algorithm. So the main thing that we need to prove is that if G divides A and B, then it also divides A mod B. This is the key observation here. So we are going to prove it. So let's say this is true. Then the common divisors for this A and B will be equal to the common divisors for B, A mod B. The set will exactly be the same of common divisors for both of them, for this and this. Now let's look at the proof. So what was our statement? If G divides A and B, then it also divides A mod B. So let's write A in this format, B into Q plus R. Remember, R is ultimately A mod B, right? That is the remainder. So R can be written as A minus B into Q. Simple. Now remember, G divides A and B. So we can write A as G into X, some X, random X. And B can be written as G into Y, some random Y. Now G can be taken as common and we have something like this. G actually divides R. So if there exists a G that divides A and B, then it must divide R, which is A mod B. Very, very simple proof, right? And this proof can lead us to this particular recursive solution. GCD of A comma B, if B is equal to 0, then it's going to be A. Remember, by the definition we said earlier, we have already discussed this. If any one of them is 0, then non-zero value will be the GCD. Otherwise, if B is not equal to 0, then you have a recursive call to the same function where A will become B and B will become A mod B. Why? Remember, if G divides A and B, then it has to divide A mod B. That means if we create a set that contains all the common divisors of A comma B, and if we create another set that contains all the common divisors of B comma A mod B, then these two sets will be similar. Here we will have a GCD of A comma B. Here also we will have the exact same value. So to get that value, we are doing a recursion like this, and the value of B will be reducing at each and every operation, right? And ultimately you will get B as 0, then the value of GCD will be equal to A. Very clean and simple solution. If you have any doubt in this particular implementation or the proof or how exactly we got here, you can comment it, but it's very, very simple. I will reiterate it again. See, if there exists a divisor G which divides A and B both, any G, no matter what the value of G is, whether it's GCD or any other thing, then that G will also divide A mod B. What does that tell you? Let's say you have a GCD for A comma B. Then the GCD of B comma A mod B will exactly be the same. Simple as that. So we are going to write this recursion and convert it into the code, right? So if B is 0, then we will return A. If B is not equal to 0, then we will call GCD B comma A mod B. So that's the whole key observation here. If you still don't get this key observation, please do comment. I will create another video and reiterate it again by giving multiple examples and going into the depth. But I hope that this is clear. Now the question is, what would be the time complexity for this? Before diving into the time complexity, a very good observation we have here. So let's discuss this observation. So this observation says that this A mod B, right, when A is greater than B, is at least 2 times smaller than A. That means A mod B is less than A by 2. This is the key observation here. This observation will help us determine the time complexity of this particular algorithm. So how we are going to prove it? So there can only be 2 possible cases. See, B is already less than A, remember. So if B is less than A by 2, by the definition of mod, A mod B will be less than A by 2, because A mod B will be less than B and B is less than A by 2. Very simple, right? A mod B is less than B and B is less than A by 2. Hence, A mod B will be less than A by 2. And that's what we are trying to prove here. Now there is another case where B is greater than A by 2, but still remember, B is less than A. So we can write it something like this. A is equal to B into Q plus R. So Q will be 1. Why? Because 2 into B will be greater than A. This is what we have said here. Take that 2 here. 2 into B is greater than A. So Q has to be 1. So we can write it something like this. So R is going to be A minus B. Now R, remember, is just A mod B. This is the remainder, right? R. So A minus B will be less than A by 2. How? Because B is greater than A by 2. So A minus B, but B is actually greater than A by 2. That's why A minus B will be less than A by 2. So this particular observation is proved by taking these 2 cases. I hope this is clear. So time complexity will be O of log minimum of A comma B. How? If you go back to the implementation, at every single stage we are doing A mod B, and this will be reducing A by half. Remember, A mod B is less than or equal to A by 2, right? That's why the time complexity will be O of log minimum of A comma B, because at every single stage we are taking A mod B, which will be less than A by 2. So we are dividing A by half every single time. So that's why the time complexity is actually in terms of log, which is log A, you can say, or whichever is the minimum. So let's take an example. This is a very common example of finding least common multiple, which is LCM. So let's represent A in terms of prime numbers, right? So P1 to the power x1, P to the power x2, something like that. Similarly, we can represent B also. GCD is the greatest common divisor. That means a number that divides both A and B. So we need to take the prime number P1, but let's take the minimum of x1 and y1. We don't want the maximum one. Why? Because let's say here we have 2. Let's say x1 is 2 and y1 is 3. So by taking the minimum, it will divide this and this. Both of them will be divided. If you take 2, it will divide A as well and it will divide B as well. But if you take 3, A will not be divided. Makes sense, right? Because P1 to the power 3 cannot divide P1 to the power 2. Similarly, for LCM, we are going to take the maximum of x comma y, right? We are going to take the maximum of x comma y. LCM is the lowest number that can be divided by both A and B. So we need to take the maximum power of every single prime number. So we can say GCD of A comma B into LCM of A comma B is just A into B. Because we are taking minimum here, we are taking maximum here. So both of them being taken. So P1 to the power 2 will go into the GCD, while P1 to the power 3 will go into the LCM. So ultimately A into B can be represented something like this. So just by dividing A into B by GCD, we get the LCM. So LCM can also be found by this particular algorithm, and it can be done in O of log n. I hope this is clear. See, LCM A into B divided by GCD of A comma B. That's what we have done here. We are dividing it first just to avoid the overflow of the integer, but it's the same thing, right? So in this video, we went through the Euclidean algorithm for computing GCD. We went through the concept and code, right? We saw the definition of GCD. We first discussed the edge cases. Then we went through the main observation that actually led us to find the Euclidean algorithm of computing GCD. Then we saw the time complexity and we wrote a recursive code. Right, the time complexity is in terms of log. We also wrote the recursive code and we went through the most common example, which is computing LCM, least common multiple. I hope everything is clear. If something is missing, please do comment. I will make more detailed video on that particular topic.